Having gone down to the scale of atoms, we have to wonder if that's the end of the progression, or is there something more? So let's consider substructure. Experiments at physics installations, and particularly accelerators, during the 1960s and 70s showed that atoms are not simple and fundamental. Not just the protons and neutrons and electrons that compose an atom, but the protons and neutrons themselves were made of smaller particles that were named quarks in the 1960s. Quarks have fractional electric charge, first particles ever found to have fractional charge. And since we only see normal matter with integer units of charge, they actually are typically found in pairs. Electrons in these experiments did appear to be point-like or fundamental. So in the size scales on the right, you can see that compared to the size of an atom, the nucleus itself is 10,000 times smaller, the proton is 100,000 times smaller, and quarks are another factor of 1,000 times smaller than that. All protons and neutrons are made of quarks. So now our sense of normal matter is that it's made of quarks and electrons, not protons, neutrons, and electrons. And going on from these experiments through the 60s, 70s, and 80s, physicists ended up with a particle zoo because they were able to create with their accelerators particles that are not part of normal matter, that come and go, or that are very hard to detect, like neutrinos, or muons, or other particles that have decay times so short they have to be produced in accelerators and trapped quickly to even measure their existence. But they are fundamental particles, and they need to be counted and considered in any scheme of how matter works. And so through this time, physicists put together the schema of elementary particles, and it's organized like this. There were 6 quarks. Normal matter, protons and neutrons, are made of the up and down quarks on the top left of this schema. But there are 2 other families of quarks, the charm and strange, C and S, and top and bottom quarks that were discovered through the 80s and 90s. These 6 quarks are the hadrons, or heavy particles. They also found there were 6 light particles. The familiar electron you can see, its heavier cousin the muon, and its even heavier and quickly decaying partner the tauon. The tau particle is very massive compared to the electron and disappears in a tiny fraction of a second if it were free in the lab. Each of these leptons, or light particles, has a counterpart neutrino, tiny, almost massless particle traveling at nearly the speed of light and hardly interacting with matter. This is a very interesting scheme, and the natural question is, where does it come from? Physicists also found 4 fundamental forces in nature and speculated about what carried these forces. The easy one is electromagnetic radiation, and so on the right, the force carriers in blue, you have the photon represented by gamma at the top, and that's electromagnetic radiation or light. That's familiar to us. G stands for a gluon, and the gluon is the force carrier that exchanges between quarks in the nucleus of the atom and binds together the atomic nucleus into a little fortress of mass, almost inviolable. The other 2 force carriers, the Z and the W, are responsible for weak interactions. They give rise to radioactivity, for example. So again, many questions arise from this diagram. Each of these particles also has an antiparticle pair, so you can really double the number of these particles from 12 to 24. It's neat to arrange it this way, but it's not very simple, and so physicists wondered that there might be a deeper scheme for this, or reason for this scheme to be arranged this way. Why are there 3 families of particles? Why do the masses of the different vertical rows change so dramatically? Why are there neutrinos? Why are there 4 forces and not more? And there was speculation going back to the 1960s of a mechanism that might give rise to the property of mass itself. And that, in the theory at the time, was called the Higgs boson. Well, we can start by at least explaining what the Higgs boson is.
If you've been paying attention to the news lately, you've probably heard a lot about this Higgs boson, or the God particle. But what exactly is Higgs boson? Well, you probably know that all matter is made up of atoms, and all atoms consist of nucleolyses, protags, and electrons. So what keeps them from bouncing all over the place? Higgs boson. Brendan Higgs was a Dutch sheep herder who had a weakness for drug-induced hallucinations. During one of his more severe acid trips, he thought he saw a large bison chasing and devouring his sheep. It was then that he had a eureka moment. He compared this imaginary bison to a then unproven particle that kept the nuclealyses, protons, and alexas in check. And until very recently, Higgs Boson was merely a theory. But the magical tubes in a laboratory called CERN proved this theory when they smashed rocks together so hard that the resulting sparks resembled the shape of a bison, thus proving the theory. So why do so many people refer to Higgs Boson as the God particle? Well, that's easy. When scientists first heard of the theory, they all shouted in unison, "God!" Why didn't I think of that? So there you have it, the true story behind Higgs Biscuit. Don't trust the media or Wikipedia or your stupid science teacher. Trust me, the guy who makes YouTube videos.
Well, maybe that wasn't clear. Let's hear it again. This is in cartoon form, but this is more scientifically accurate.
And so one of the things people predict is the Higgs boson. The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things that have mass means it has stuff to it. It's not actually stuff. Earlier I was saying an electron has mass, but has no volume. How can that be? Turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons, some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when two things both have mass, they attract each other. Interestingly, you can't have negative mass or repulsive gravity. So gravity is different from other forces that way. The Higgs theory starts with this. Imagine a field that permeates the entire universe. And every particle feels this field, is affected by this field in different amounts. So some particles are really slowed down by interaction with this field, like swimming through molasses, and other particles hardly feel it. So the ones that hardly feel it, they have a small mass. The ones that are really affected by it, they couple strongly to this field, are slowed down a lot, they have a large mass. So you've turned the question of why do particles have different masses into a different question. Why do particles feel the Higgs field differently? But there is one manifestation of the field is the existence of this particle.
This is a very strange situation. The physicists have essentially done a judo move and have taken our idea of mass or stuff and turned it into something else, about how mass is an attribute that's caused by a field, something that permeates space, and that our sense of mass is caused by interactions with this field. And the carrier of this field is a particle called a Higgs boson. So having come up with this idea, which had some attraction to physicists at the time, they set off to find the Higgs particle itself. Just to make this a little clearer, let's follow this analogy again of the dinner party or the cocktail party. Imagine a room full of people. They represent the field. The field permeates space. It's invisible. We don't have to see it. We watch it by its interactions. Imagine a celebrity, Einstein say, walks in and he represents a particle. His interaction with the field is what generates mass. Einstein will attract a lot of attention and be slowed down by all the people wanting to talk to him and shake his hand, so we can think of him as a massive particle. Somebody who nobody wanted to know and wasn't very good looking might just walk through the room almost without notice, and so they'd be a low mass particle. So you see the analogy. Also, imagine this same room again, and now imagine someone just releases a rumor at one end of the room, and the rumor passes through the room. A cluster of people discussing it is the Higgs boson. So here we have an analogy for the Higgs field, an ambient field that interacts with particles to give them their mass, and the Higgs boson, which is the mechanism by which it does so, which we might identify, and identify with an accelerator, as indeed happened in 2013. I hope after this you do finally understand the Higgs boson. Don't worry, most people don't, but I think this is a good enough primer that you should get the idea. And so again, we have this schema, the 6 quarks in 3 families, the 6 leptons in 3 families, the 4 fundamental forces, and the hypothetical, but eventually discovered, Higgs boson that ties it all together. The world is not just full of particles, but it's full of interactions. So the interactions are important too. The electromagnetic radiation that's carried by light and photons, the gluons that move rapidly among the quarks and hold the nucleus together, the Higgs boson that interacts with all of them to give them their mass. So physics is not just about particles, but it's about their interactions and about the forces that cause those particles to behave the way they do. Here's the timeline for what became the standard model of particle physics, which I've just been describing. It was kicked off by the discovery of the electron, the first new particle since Rutherford and since we thought of an atomic nucleus. Photons were understood early in the century, and you can see through the 40s, 50s, and 60s, especially in the 1960s, enormous progress with accelerators on discovering the quarks and other particles and exchange particles. You can see the Higgs boson was actually speculated or theorized back in the early 1960s, and it took decades to find. So you can see why physicists were so excited in 2012 and 2013 when they finally found the Higgs boson, the last missing piece, if you like, of this standard model of particle physics. We call it the standard model as if it's all neatly tied in a bow and the end of the story, but it's not. The standard model, in the end, has 19 knobs or free parameters. It doesn't really explain the particle hierarchy, why there are 3 families of particles or why there are pairs of particles in each family, and it omits to explain very fundamental nature of gravity, because gravity is not part of the standard model, and the 2 biggest components of the universe, dark energy and dark matter, are not really explained. Also, it has trouble explaining why the universe has so much more matter than antimatter. So physicists are not done, especially with the fundamental forces, which are so different in strength. The gravity force incredibly weak, but dominating on large scales because it's universally attractive. The strong force, the strongest of all, but negligible on scales beyond the nucleus. And then at intermediate strengths, the electromagnetic force and the weak force. Why are there 4 forces? Why are their strengths and natures so different? The standard model doesn't tell us. More theory, more work is needed. And that's the challenge of particle physics. Particle physics, the use of accelerators like the Large Hadron Collider, involves trying to unify the forces and explain the masses of fundamental particles by experiment. We also hope for new physics and things we might not anticipate, such as extra dimensions, for example. Also, we might hope to solve some problems with accelerators that are given to us by cosmology and the situation of our universe. So particle collisions at this high energy frontier enable us to explore fundamental questions about nature. And that's the end of this topic.